Hello, everyone. Let's resume the meetings. So we're going to have our technical section 3 in the next hours. So the first speaker is Kieran James Barvenik. I pronounce it right, I guess. Uh, he is going to talk about the tactile sensing and the grasping through the thin shell buckling, which is a very important topic for the soft robots. I believe it's especially under the underwater soft robots, it's very important. So I'll give the stage to Kieran, and then let's just welcome him.
Can everyone hear me all right? Okay, awesome. Hello, everybody. I'm Kieran Barvenik. I'm a second-year PhD student conducting research with Dr. Eleonora Tubaldi, and today I'll be talking to you about our research in tactile sensing and grasping through thin shell buckling. As a quick note, this research was recently accepted for publication within Advanced Intelligent Systems, and although I don't think it's okay, awesome. Sorry. Although I don't think it's quite published yet, if you're interested in the research that I discuss, please keep your eyes peeled for that. Without further ado, I'll get right into it. Now, there have been a lot of amazing talks today about soft robots, and one of the areas where they demonstrate some of the most exemplary properties is within the field of soft grippers. Here, soft grippers are able to utilize the continuous deformations of soft materials to demonstrate a lot of exciting properties. For instance, the granular material gripper shown on screen utilizes the soft material to deform around the surface geometry of complex objects in order to give it a universal grasping capability. Additionally, the intrinsic softness of these soft materials enables these grippers to deform around biological tissue like the jellyfish shown on screen without risking any harm to the organism. And additionally, soft grippers can demonstrate highly programmable responses, which is exemplified by the kirigami gripper shown on screen, for which small changes in the initial geometry will create large changes in the deformation response. Now, historically, soft grippers have been criticized for their diminished actuation speed and actuation force relative to their rigid counterparts. However, in recent years, this is being mitigated through the introduction of mechanical instabilities. Mechanical instabilities like buckling and snap through have historically been considered failure mechanisms for metal components. If you imagine like a beam truss, buckling would definitely be a failure mode for that. But for soft materials, they're able to undergo these large scale deformations repeatedly without ever plastically deforming. And one example of this is through the snap through gripper on screen, which utilizes the snapping of a spherical cap in order to produce a rapid actuation. So all of these grippers that I've shown here demonstrate very interesting properties, but there are still interesting avenues going forwards in order for us to find ways of combining the most interesting and exciting properties of soft grippers into unified versatile frameworks. And this is what we aim to answer here. And more specifically, for objects with complex surface geometry, how can we grasp them with tunable input and output forces and protect them against external disturbances, all the while sensing information about the environment? And in order to answer this question, we turned to the iconic video game character Pac-Man, and more specifically, the clasping and unclasping motion of the character's mouth as he moves around the stage and gobbles up pellets. Although the interesting thing to note here is that nature has actually implemented a similar shape in the form of the predatory tunicate, which is a deep sea organism which utilizes a large almost hemisphere-like oral siphon in order to provide an energetically favorable system for collapsing around and engulfing prey. So how do we actually achieve this physically? We do this through the use of our hemispherical Pac-Man grippers. These are made of two key components. The first is a slightly stiffer Elite Double 32 hemispherical shell, which we adhere to a thin Ecoflex membrane at the equatorial line of the hemisphere, which creates an isolated fluid cavity. When we deflate the fluid cavity, it triggers a buckling reconfiguration at a particular critical pressure value, which triggers the so-called Pac-Man deformation shape, where two lobes pinch together, which is highly conducive for grasping and manipulation tasks. Now, when we began our research, we wanted to find some closed form analytical solution that would tell us how the critical buckling pressure of the structure, or the pressure value at which the structure would demonstrate this Pac-Man reconfiguration, how that pressure value connects to the geometric parameters like the slenderness ratio, or the ratio between the thickness of the shell to its radius, and the cap angle. However, we noticed when we were trying to look for this that there was a large gap in literature, and more specifically, the buckling problem for a spherical shell with a clamped edge boundary condition has been studied in the literature, but a free edge actually introduces a lot of complexity. And so in order to study this particular geometry while kind of sidestepping the issue of the shell buckling problem, we decided to develop a simplified two-dimensional analogy instead of solving the full problem. And to do this, we envision the hemispherical shell as a circular arch with the properties of the equatorial line of the hemisphere. When we do this, its radius becomes a projection of the radius of the full hemisphere, and we're able to look for classically tabulated solutions for the buckling pressure of a circular arch, and we get this nice and neat relationship between that buckling pressure and the geometric properties of the structure. We can compare this to numerical results. And here on screen, I've demonstrated the critical buckling mode of the structure when we examine it within a finite element software like Abacus. And if we do this, we can also collect the pressure values and compare them to our analytical model. When we do that, we see quite excellent agreement between the structures, especially given that the analytical solution we used is a two-dimensional circular arch instead of a full solution to the shell buckling problem. Both demonstrate the same scaling factor between the buckling pressure and the slenderness ratio, and the scaling is very similar between them as well. Additionally, if we look at the effects of varying the cap angle, we can see that the introduction of the cosecant term in our slenderness ratio gives us a highly matching curvature between the numerical and the analytical results as well. This closed form analytical solution is useful for us because it provides some design insight into how we can impact the buckling pressure, or the pressure at which we observe this reconfiguration, by controlling the geometric parameters. However, in order to actually apply this uniform pressure to the inner surface of the hemispherical shell, we need to add a thin ecoflex membrane to that equatorial line in order to create an isolated fluid cavity, so then we can leverage fluid pressure to apply that inner surface pressure. When we do this, we lock the cap angle to be 90 degrees to simplify the design space that we're exploring. However, we introduce a new parameter that we can vary in the form of the film thickness ratio. If we vary these two parameters independently, we can explore the resulting critical buckling pressure numerically, which we get this complex surface. Once again, this is a useful design tool because we can plug in certain geometric parameters and find the buckling pressure at which the structure will reconfigure. However, an interesting point to note about this surface is that there are two sharp creases in it, which essentially bisects the design space into three clear regimes. The first is what we call the destructive buckling regime. This is when the stiffness of the film is much higher than the stiffness of the shell, such that it essentially acts like a clamped edge boundary condition on the shell, and the shell exhibits the classical dimpled buckled mode shape that we would expect from a clamped hemispherical shell. Here, the equatorial line of the hemisphere does not deform meaningfully, and it's not so useful for grasping tasks. But the second regime is what we call the destructive or the constructive buckling regime. This is where the film stiffness and the shell stiffness are comparable and both deform in unison to give us that Pac-Man grasping shape that we desire. The last regime is a so-called film deformation regime, which is where the film is so not stiff compared to the shell that it deflates fully before there is any meaningful deformation of the equatorial line of the hemisphere. We've talked a lot about numerical results. However, we can also observe these experimentally and compare them to the numerical results. And here on screen, I first have the destructive shell buckling regime. The plot that is being updated live is a pressure versus volume curve of the fluid within the fluid cavity of the hemisphere. And we can see that once the dimpled mode shape appears within the system and propagates through it, there's a sharp drop in the pressure volume curve of the hemisphere. Next, for the constructive buckling regime, we can observe that the moment when the pattern reconfiguration that we're looking to excite triggers, which is signified by a sharp change in the slope of the pressure volume curve, which you can see in both the numerical and the experimental results. And lastly, potentially the least interesting regime is the full film deformation regime. And here we'll just observe that the structure does not really reconfigure meaningfully by the time we have undergone our full deflation procedure here. Now, one reason that I'd also like to emphasize that it is beneficial for us to use this buckling pattern reconfiguration as a basis to develop soft grippers is that it's scale independent. And so here are a variety of different sizes and materials that we've used to develop similar soft grippers that all demonstrate the same pattern reconfiguration. So this arises fully from the geometry of the structure rather than the particular materials that we've chosen. However, there are a lot of soft grippers that exist within the realm of the literature right now. And so a question that we still have to answer is, why would you use this gripper as opposed to any other gripper? And the answer to that actually comes from its sensing characteristics. Here, we're going to demonstrate that by observing just one pressure sensor measurement, which connects to the isolated fluid cavity within the hemispherical gripper. On the plots that are evolving on screen, we have the dashed line, which is a reference curve that's collected when the gripper is not interacting with an object. And we compare that to 3 trial curves, which are taken when the gripper is interacting with objects of different sizes. And what we can see is that the interaction between the soft structure with a rigid object creates a measurable difference in the volume of the cavity, which then influences the pressure that we read. This means we can get an idea of both when we've contacted an object and the relative size of the object just by monitoring one pressure sensor reading, which again is attached to the isolated fluid cavity that we already need to impose on the structure in order to actuate it in the first place. We can play a similar game to detect the moment that the lobes of the gripper actually contact the object that we're interacting with. Once this happens, the presence of the object obstructs the continued deformation of the hemisphere into its first mode shape, and we see a sharp change in the slope of the pressure volume curve. And lastly, we can do the same thing with the release of the object. When the trial curves collapse back onto a reference curve, we know that the object has been released from the gripper's grasp. And so we can use this simple control theory in order to detect points for grasping objects of a variety of different sizes, shapes, and stiffnesses. Here it's a bit hard to see, but that was the gripper grasping Jello. We've also done the same thing with it grasping tofu, a raspberry, screwdriver, and a handful of other objects that we have done in the publication. Now, again, this is all done from monitoring just that one pressure sensor value, meaning that we haven't had to add any additional manufacturing complexity in order to understand these environmental interactions. And so the entire manufacturing process is extremely simple. Additionally, the control rule is, or the way that we actually detect these key points from the data is very simple as well, with it legitimately being us comparing the difference between the reference and trial pressures. So it's very easy to implement from a code point of view as well. Another interesting facet of this particular soft gripper design is that the entire body of the gripper is wholly soft, meaning that we can deflate the structure fully and feed it through cavities or openings that are much smaller than the diameter of the gripper itself. This could be useful or interesting for applications maybe in the world of medical robotics, where you might be operating within highly constrained environments, and you want a gripper that can be fed through those environments, perform some kind of task, and then be removed afterwards. Here it's just going to deflate and pull back through the fluid cavity. And lastly, we can use it. I don't know this one. The opacity is pretty low on this one. But this is a demonstration of the gripper being used underwater. I won't mess with the slides too much here, but essentially you can use water as the operating fluid as well, and it works just as well. However, like this gripper, like any other gripper in existence, has some limitations. It can't grasp everything. And there are some objects of particular sizes and shapes and weights that the gripper is just not designed to grasp properly. This is a particular 3D printed statue of our university's mascot, Testudo, and the gripper just isn't designed to grasp these objects. And so for these particular cases, what we wanted to answer next is how can we slightly alter the geometry of the soft gripper in order to change its deformation geometry as well as the gripping force in order to be able to grasp these objects of different sizes and shapes. And more specifically, what we're going to look to do is we're going to look to change from this 2-lobed deformation shape, the Pac-Man shape that I've been talking about up to this point, to a 3-lobed deformation pattern like the one shown on screen. Notably, since this is a buckling response, we could do the same thing for 4 lobes or 5 lobes or any higher number, but for now we're just going to stick to 3 to keep things simple. When we think of adding stiffening elements, which is how we're going to change the geometry here, we can think of the most extreme case, which is adding a stiffening element that's so much stiffer than the soft robot that it essentially acts like a new boundary condition. And this is where we started our investigation. Here, we're exploring the numerical results that occur when we fix 3 longitudinal lines around the body of the hemispherical shell. And when we do this, we don't observe the nice 3-lobed deformation shape that we were hoping to. Instead, the shell kind of crumples in a frustrated and unpredictable way near the equatorial line. So next, we tried pinning longitudinal lines around the hemispherical shell. However, we observed the same thing. But if we pin only equatorial vertices instead of those full longitudinal lines, the structure then wants to deform into that predictable three-lobed shape that we were looking to excite in the first place. So this is good news for us. However, in truth, we don't want to add an extremely stiff element to the soft robot because that could compromise the structure's softness in general. And so instead of pinning these nodes, we're going to instead impose an elastic connection between the center point of the gripper and those equatorial vertices. And thankfully, this process is pretty straightforward to accomplish with our manufacturing process. Since we usually manufacture the hemispherical shell separately and then adhere it to the thin EcoFlex film through the use of a simple 3D printed well, we can simply embed a higher stiffness element into the EcoFlex well and cure them all together. And it's a very straightforward process. This does, of course, create a very complicated design space that we could theoretically sweep over, including varying the material, size, number of lobes of the stiffening element. However, for the time being, we're just going to demonstrate this through the use of a single type of stiffening element. Here, I've highlighted it on screen because it can be a little bit tricky to see, but once it disappears, hopefully you can see the stiffening element in place on the structure. And what we see when we deflate this, both experimentally and numerically, is that the quantitative and qualitative agreement is quite excellent. Now we can revisit the grasping trial that we conducted and the gripper originally failed at. With both our two-lobed and our three-lobed gripper. And while the two-lobed gripper fails to grasp the turtle, the three-lobed gripper is able to grasp it quite efficiently. So this is very exciting for us. It shows us that we have a simple and repeatable way of changing the deformation geometry of the soft gripper without really significantly impacting the manufacturing process. Another important question comes up, which is when would you want to change the geometry of the gripper? How would you know that you need to change the geometry, which is a great question. And one of the ways that we're looking to expand upon that is through a more rigorous experimental campaign where we test the soft gripper on a variety of objects of different sizes, materials, and shapes in order to, first of all, determine the sensing performance of the gripper and how accurate and consistently it can detect the different characteristics of each object, as well as determining the grasping accuracy and performance, which would then give some indication of when you would want to change the geometry of the soft gripper. That about brings me to the end of the talk. I'd like to briefly acknowledge Dr. Tibaldi's help, as well as Zachary Coogan. He's one of the master's students who's helped a lot with this research, and one of our colleagues from Aarhus University in Denmark, Matteo Pizzula, has also helped a lot as well. Yeah, with that, I'd like to wrap things up. Thank you.